well if you wish. But if you want to start the recording separately, that's fine. Just do so.
I think it's good if you're recording, then I think that should be good.
Yeah, no problem. It has started, so all of this chitter is on the recording. It's a great pleasure to welcome Cole Fury to join us today. She is joining us virtually, and she tells me she's coming to us from Utah. So thank you very much for agreeing to give this talk. The standard model is, of course, of significant interest to everyone here, and we're interested in especially your connections with the octonions today, which anyway, I'll hand over to you and stop rambling.
Thank you. Well, thank you so much, Denjo. So, first of all, I want to say thank you very much to Denjo for inviting me to come speak with you today. So Denjo's collected a lot of really great speakers in this series, and so I'm glad to be invited. So today my talk is based on joint work together with my collaborator, Beth Romano. Beth is a pure mathematician, recently at the University of Oxford, and now she just recently accepted a lectureship at King's College in London. All right. Okay, so today I'd like to tell you about our current efforts to describe the standard model's particle content using only the real numbers, the complex numbers, the quaternions, and the octonions. Now, as you know, the standard model is rooted in a particular gauge symmetry, and this symmetry is given by a strange-looking Lie group, SU3 cross SU2 cross U1 over Z6. And we're going to call this gauge group GSM. Now, nobody seems to know why nature has chosen this group over any other group. When constructing the standard model, we don't derive the gauge group from first principles, but rather we introduce this as an initial assumption. Now, the problem in figuring out where the standard model symmetries come from is already daunting enough. But in fact, it's not the hardest problem to solve in the standard model. A harder problem is trying to understand where the standard model's particle content comes from. Particles in the standard model are given by irreducible representations of GSM. But the group SU3 cross SU2 cross U1 over Z6 has an infinite number of irreps. So how do we know which irreducible representations to choose? Well, within the energies we can probe, nature seems to have made a clear choice. So this is the standard model's particle content. First, we label how they transform under SU3, then how they transform under SU2, and then how they transform under U1. For example, here we have left-handed up and down quarks, which transform as a triplet under SU3, a doublet under SU2, and which have a U1 weak hypercharge of 1 over 6. Now you'll notice that I've written a subscript 2 here, and the 2 is to indicate that we need 2 copies of this representation so as to account for how these particles will transform under space-time symmetries. So next here are right-handed up and down quarks, and you'll notice that right-handed fermions live in different representations than their left-handed counterparts. We say that the standard model is a chiral theory. Okay, so if we continue on, here is a first generation of fermions, and a second generation, and a third generation. So I should mention that strictly speaking, the standard model has no right-handed neutrinos, but many models do include them, and we're going to include them later on. Okay, so that's the standard model's fermion content. And next we want to describe gauge bosons, which live in the adjoint representations of the standard model symmetries. And finally, we have the famous scalar boson given by the Higgs. Now, needless to say, this is a very long and arbitrary looking list of irreducible representations. And when we add up the total number of real, off-shell, unconstrained degrees of freedom, and when we include right-handed neutrinos, then the total comes in at 244. So it's hard not to look at this and wonder, could there be some unifying mathematical structure which ties all of these irreducible representations together?
So
now we're in
You have a blueberry crayon thing just in front of part of the screen. I think
I do.
Maybe you can move it a little bit. It's showing up for us for some reason.
I see. Okay,
Yeah,
it wasn't showing for me. Is it gone now? Okay.
Yeah.
Is that better? Okay. Yeah. Thanks for letting me know.
Yeah, that's perfect. Yeah. Sorry.
Yeah. No, it's better that you told me. It's strange that it didn't show up for me. Okay. All right. So this is the standard model's particle content, and when we add up all the degrees of freedom, including 3 generations of right-handed neutrinos, the total comes into 244 real. Okay, so we're now in a position to tell you the problem that Beth and I are trying to tackle. That is, Beth and I would like to see if we can fit this long list of irreducible representations into a single algebra. And furthermore, we'd like to see if this algebra can somehow be generated using only the real numbers, the complex numbers, the quaternions, and the octonions. As you might imagine, it would be quite a stunt to demonstrate a simple transformation rule, which has all of these vector spaces simultaneously transforming in the right way. Now, throughout the seminar, we're going to be talking about the real numbers R, the complex numbers C, the quaternions H, and the octonions O. Now, the thing I find most appealing about these algebras is not so much the fact that they're special. Of course, they're known to be the only finite dimensional norm division algebras over the reals. But more so, I find them appealing for pragmatic reasons. That is, in nature, for some reason, they seem to be largely unavoidable. For example, you'd be hard-pressed to find a theory in physics that doesn't depend on the real numbers in some way. You know, we're so used to always writing down, we're so used to using the real numbers that we don't realize that we're making a choice in number system anymore. And likewise, the vast majority of quantum theories are built using the complex numbers. And whether physicists realize it or not, it's quaternionic structure, or more precisely complex quaternionic structure, that underpins special relativity and electromagnetism. Now, one person to point this out early on was the Irish mathematician, mathematical physicist, A.W. Conway in 1937. Furthermore, the octonions have been useful for teasing out properties of the strong nuclear force now for decades. As far as we know, it was Murat, Grenaydin, and Fezzik-Guerci who were first to point out that the octonions were good for describing SU3 color transformations in quarks back in 1973. So in summary, these norm division algebras provide one rare example of a set of number systems that is simultaneously unique and yet still woven into the fabric of everything that we see around us. It's for this reason that we're going to build our models from only these algebras. So there's one final comment I wanted to mention, that the quaternions were discovered in 1843 by Hamilton, who was an Irish mathematician. That same year, the octonions were discovered by Graves, who was also an Irish mathematician. And so between Conway, Hamilton, and Graves, Irish mathematicians have pioneered much of the early studies of these number systems. Okay. So not long ago, a collaborator of mine, Mia Hughes, and we worked out a model based on the algebra Rcho. So Rcho is the tensor product over the reals of the real numbers, the complex numbers, the quaternions, and the octonions, or equivalently, they're the tensor product over the reals of just C, H, and O, as the R here is included trivially. So Rcho is also known as the Dixon algebra, after Geoffrey Dixon, who found this algebra independently already a few decades ago. Now, Rcho is 64 real dimensional, and it so happens exactly the size of one generation of fermions. That's when you include a right-handed neutrino. So Mia and I demonstrated a model that identifies one generation with a single copy of Rcho. In fact, this was the first time that such a single copy model had been built that also extends an earlier result from Grenaydin and Guerci In the 1970s, Grenadian and Gersey identified up quarks with a subset of the octonions. However, we'd like to move the goalposts, so to speak, so that we're not aiming to describe just one generation, but rather three. And furthermore, we'd like to include all the standard model's bosons as well. So how are we going to do this? RCHO is only a 64 real dimensional algebra, but ultimately we want to be able to describe 244 real. So where's this extra space going to come from? Well, one idea is to take a hint from nature. Nature succeeds in describing the entire human genome using only 4 bases, A, C, T, and G. Well, how does it accomplish this? Nature accomplishes this not by considering these 4 bases alone, but rather by considering sequences of the bases. So let's see what would happen if we were to consider sequences of RCHO elements, one being left multiplied onto another. Might we be able to encode the standard model's particles using these sequences? Now, sequentially left multiplying RCHO elements onto RCHO elements generates something known as its left multiplication algebra. And we're going to call this left multiplication algebra LCHO for short. Now, for physicists, there's a limited but familiar analogy that might help in understanding what the left multiplication algebra is. Now, very loosely speaking, you can think of the left multiplication algebra as a space of operators in quantum theory. The original RCHO element being multiplied is like a state in a Hilbert space. So in a sense, by studying the left multiplication algebra, we're turning our focus away from the original Hilbert space, and we're focusing instead on the operators. Okay, so here's how we define the left multiplication algebra in detail. So suppose we were to multiply our 2 RCHO elements together, y and z. Loosely speaking, you can think of course, you can think of the y as the operator and z as the state. Then we can see that left multiplying y onto z induces a complex linear map on z, and this map is commonly known as L sub y. So just like operators, these complex linear maps can be composed, which is how we're going to define multiplication. We can also take linear combinations of these maps. So we define LCHO to be the sub-algebra of RCHO's complex endomorphisms, its complex linear maps, which are generated by the LY.
Excuse me, can I ask you a question?
Yeah.
How does one make observations? What is the Hilbert space and what are the rules of observation, experimental observations?
Okay, so good question. So at this point, I'm just using it as an analogy. But we are going to get into that later. I'm going to define what the states are, and I'm going to be able to say something near the end about projective measurements.
There was already long ago some discussion of Hilbert spaces over quaternions, I think by Finkelstein, and it got stuck at some point.
I see. Yeah.
So
yes. So in this. Oh sorry, yes. Okay. So in this case, the states are going to end up living in this in the Hermitian part of this LCHO algebra.
It has to be a complex linear map, no? It has to be a complex linear map, which is identity.
Exactly.
Linear positive map. But what is it? Does it exist?
So the space that we're going to be interested in is going to be over the complex numbers.
But it has to acting on an element of the algebra, it has to give a complex number, which is so. Is this a star algebra?
It presumably is, yes.
In fact, it is. It's a C-star algebra. It is, and so I'm going to define a Hermitian conjugate, or what we're going to call a Hermitian conjugate on that space. exactly.
What is star on O?
It's coming. I'm sorry.
What is a star operation on O?
So I'm going to define this. I'm going to define it's an anti-involution, and it's coming up in the next slides.
Okay.
Okay.
So you basically your algebra here is a set of entries. I mean, you've got 4 entries. I can think of it as separated into 4 commas.
That's a good question. That's also coming up.
Okay,
so there's different ways to think of it, and
yes, I appreciate that.
There's a sense in which instead of, this is a good question. There's a sense in which instead of 4, the A, C, T, and G, there's actually 8.
Somebody, let me see if I can find the culprit here. Sorry, I'm just muting people.
Just randomly muting people.
Yeah, just there's a noise coming from somewhere there, so I'm muting anyone that was open.
Okay.
All right.
You said this is a C-star algebra. C-star or complex numbers?
Yes. So you'll see in the upcoming slide, I'm going to define a Hermitian conjugate, and it relates to the complex numbers.
And what about associativity?
We'll give her a minute. Perhaps we'll give her a minute to get onto the next 2 slides or something, because I think we're asking just ahead of time.
So the associativity I can answer right now. So I'll just move back here. Multiplication, as I just mentioned, is defined by composition, and composition, as you know, is associative. This is in fact an associative algebra. Yeah, exactly. So I think that's the best thing to say, is that this is an associative algebra. You can think about when you're left multiplying elements of RCHO onto themselves, you can think of it as there's kind of like 2 algebras happening at the same time. There's the original RCHO algebra, which is being multiplied, and you can, again, very loosely speaking, think of it as operators being applied to the state. So you start with a state Z, and you multiply a Y onto it, and that gives you a new Z prime. And that's kind of, you can think of that as being the original RCHO algebra. But there's simultaneously a compatible algebra, which is also happening at the same time, and that's this left multiplication algebra. And there, the concept of multiplication is composition of maps. And these 2 things are happening at the same time. Just like in quantum theory, how you can compose 2 operators, you can have an operator act on a state to give you a new state, or you can compose 2 operators. You can have compose one operator with another to give you a third operator, and that's an associative operation. So right now we're concentrating on the left multiplication algebra, and the multiplication rule here is composition, and so that is in fact associative. And it's a good thing that it is, because that's how we're going to, there's Clifford algebra structure that comes out of this. Clifford algebras by definition are associative.
So you lose some of the properties of the octonions then?
It's not, it's a different, it's another algebra that's happening at the same time. So there is octonionic structure that we're going to use that's going to also come up later in the talk.
But you couldn't recover the octonions from a faithful representation of this structure.
So this is, so I'm not claiming that this is, what I'm saying is that this is a natural structure that shows up when you're multiplying octonions or RCHO. It's there whether you like it or not. And what we're doing here is we're focusing on this space for reasons that are also going to come up later in the talk.
And I guess it's not an abelian algebra, is it?
That's right. It's non-commutative. Yeah. Okay. So where were we at? Okay, so we just defined this algebra. So to give you another, this has a similar flavor to, for example, if you calculate a scattering amplitude in quantum field theory, where you can put everything into the operator space. You can put creation and annihilation operators. You can kind of ignore the Hilbert space in the sense that you just trivialize it by turning it into the vacuum, and then all of the interesting stuff somehow happens in the space of operators. It has a similar flavor to that, I would say. Okay, all right, so here is the left multiplication algebra. And right, so in the case of RCHO, its left multiplication algebra turns out to be isomorphic to the 16 by 16 complex matrices, or alternately isomorphic as a matrix algebra to the complex Clifford algebra CL8. Now, as you know, the Clifford algebra CL8 is generated by a minimal set of 8 elements, which we're going to call gamma J. And loosely speaking, you can think of the 8 gammas as analogs of the 4 A, C, T, and G bases of genetic sequences. That is, these 8 gammas give the smallest possible set needed to generate the whole left multiplication algebra. Okay, so let's pause to summarize where we're at. We'd like to embed the standard model's long list of irreducible representations into a single algebra. And furthermore, we'd like this algebra to be generated in some way by the real numbers, the complex numbers, the quaternions, and the octonions. Now, when we fused these RCH and O together into the tensor product RCHO, it gave us a 64 real dimensional space, which is sadly too small for our purposes. So here we're proposing instead that we take a hint from nature's efficient encoding of the human genome. That is, instead of looking at RCHO itself, perhaps we could consider the space of sequences of RCHO elements, left multiplying RCHO elements. These sequences.
Sorry, called the 64 is really just treating the in Mat 60. It's Mat 8, I suppose. Is it?
I'm sorry.
Where is the 64 sitting in Clifford 8? Is it just one vial representation of it or something like that?
Right. So
there's a natural 8 by 8 floating around.
Yes.
I mean,
it's the left so we're talking about the left multiplication algebra on RCHO. I think
it's treating it as a module. It's treating that as a module. So
I think that perhaps the easiest way to look at it, which we'll also come to, these are really great questions, which you come to at the end of the talk, is at the very end, we're going to consider both left and right multiplication, in which case, then that will give us a CL10. And that in that case, then the full multiplication algebra gives you all of the complex endomorphisms of that space.
Okay, thank you.
Yeah, no
we'll
problem.
wait in anticipation for more.
Yes, yeah. Oh no, I'm thrilled that you're anticipating. Everybody seems to be anticipating all my coming slides, so I think this is good. Okay, right. So instead of looking at RCHO itself, perhaps we could consider the space of sequences of RCHO elements, left multiplying RCHO elements. And these sequences of RCHO elements form their own algebra, which are known as RCHO's left multiplication algebra. Now, RCHO's left multiplication algebra is isomorphic to the complex Clifford algebra CL8. And loosely speaking, you can think of CL8's minimal set of 8 generators, gamma J, as being the analogs of nature's 4 bases, A, C, T, and G. Okay. So now, as you can check for yourself, our left multiplication algebra is 256 complex dimensional. And what we need, as we mentioned before, is 244 real. So it looks somehow like we're going to need to cut our space roughly in half. Now there's a natural anti-involution on RCHO's left multiplication algebra, which is going to come to the rescue. It's the map that reverses the order of multiplication and which sends the complex imaginary unit I to minus I the quaternionic imaginary units epsilon j to minus epsilon j, and the octonionic imaginary units ek to minus ek. So we're going to call this map the Hermitian conjugate on RCHO's left multiplication algebra. And we can get away with calling it a Hermitian conjugate because you can show that this map is equivalent to the Hermitian conjugate on 16 by 16 complex matrices. Okay. So we're going to be interested in the Hermitian subspace of RCHO's left multiplication algebra. So this is the algebra we're going to focus on. Because, as you may know, Hermitian matrices have all kinds of important applications in physics. And in particular, H16C can be thought of as an extension of H2C, which is how many modern formalisms like the spinor helicity formalism describe their form momenta. Furthermore, it's easy to see that this Hermitian space is 256 real dimensional, and this is now quite close to our goal of 244. Okay, so for the majority of this talk, we're going to be interested in this H16C generated by the division algebras. And a very good question you might ask at this point is, well, why didn't you just start with H16C in the first place? And there are two answers to this question. So first of all, H16C is a 256 dimensional space, which is quite a large algebra. Ideally, it would be nice to begin with smaller building blocks.
But it naturally has Clifford 9 acting on it. So
there's Clifford 9 on H16C. Okay, I'll take your word for it. Let's see. Right. So it would be. I would say it would be nice to have a mathematical model, much like the game of chess, that is where a simple set of rules can lead to complicated outcomes. Now, the other reason why we choose not to just start with H16C from the beginning is that H16C on its own is just a featureless box. It has no substructure. However, when it's generated by the division algebras, it instead has a rich substructure. And we're going to make use of some of this extra substructure now. Okay. So for reasons I will explain in detail towards the end of the talk, the multiplication algebra of the octonions readily introduces a set of 4 mutually commuting idempotents, which may be thought of as generalizations of chirality projectors known to physicists. So here's a sample of what those idempotents can look like. We're going to call these idempotents little s star, capital S, and capital S star, where the star here denotes the complex conjugate. So clearly you can see that all 4 of these idempotents originate from a single octonionic imaginary unit. And thanks to a special property of the octonions, which we'll also describe later on, they all happen to live in the left multiplication algebra of RCHO. Okay. So here is the Hermitian part of RCHO's left multiplication algebra. It's isomorphic to the Hermitian matrices H16C. Now, when we apply these 4 octonionic idempotents to our H16C,
sorry, what did the R refer to in your previous slide? I got the L was associated with the left.
Exactly. Yeah, good question. Nice catch. That is right. So L refers to left multiplication, and R refers to right multiplication. So there's something that is a little bit surprising here about the octonions, that when you right multiply, this will come up again later, when we right multiply any octonionic element onto another octonionic element, you can always re-express that map by using only left multiplication. And this is a bit of a surprising feature of the octonions because it's not true for the quaternions. it's also true. It is true trivially for the real numbers and the complex numbers because they're commutative algebras.
Okay, thank you.
Yeah, good question. Okay, so here is our H16C. And now when we apply these 4 octonionic idempotents to our H16C, it partitions the space into blocks like this. So within the theory of Jordan algebras, such a partitioning is known as a Peirce decomposition. So the question that Beth and I have been working on lately is, can we find a simple transformation rule that will make these Peirce blocks transform like the irreducible representations of the standard model?
Can I ask a question? I'm a bit confused. What are the observables of the system? Experimental observables. What do I see? Okay. Are they over this as an underlying field?
That's it. So that's a really good question. So with this Peirce decomposition, so are you familiar with Peirce decompositions?
No.
Okay, so a Peirce decomposition, it's familiar within Jordan algebras, and it's basically if you take a Jordan algebra like this H16C is a Jordan algebra. You can the Peirce decomposition is defined using a set of projection operators like what we have here, and those projection operators. So that it has to be a set of orthogonal projection operators which sum to 1. And that's exactly how projective measurements are defined.
But they observe, for example, in quantum mechanics, the operators have an infinite spectrum. Okay, for example, position operator, moment. Here it looks like finite dimensional. Am I wrong?
Yes, yeah. So yes, yeah. So at this point, everything I think it's fair to say that we're going to be dealing with finite. Finite quantum numbers. We're not going to, So I'm not, going to claim to reproduce all of physics here.
Okay. Also, the standard model, the observables are infinite dimensional. For example,
yes.
Sure. You don't get them. At least I don't see them.
Exactly. So this is not at the level of being a quantum field theory. We're just dealing with the standard model's irreducible representations at this point. For its internal symmetries. Yeah, good question. Okay. So right. So, but this is actually something that is I find is actually quite nice about using Peirce decompositions, is that you have a Peirce decomposition is defined using an orthogonal set of projection operators which sum to 1. And this is exactly how projective measurements are defined. So there is a direct connection to projective measurements here.
So can we read off the dimensions of the ranks of the projectors from this?
Yes, you could, you could. I'm not I don't have this memorized, and I wouldn't be able to say this. But in principle, yes, I think you could.
I mean, presumably you've drawn them as some of them are smaller. They're lower ranked. They don't all have the same rank as projectors, I presume.
Exactly. That's exactly right. So yes. So the boxes in this space are all of different sizes. Yes.
To define the rank, you need a representation on a Hilbert space. At least the one I know. But here there is, at least I can't see a representation of this algebra or a Hilbert space.
She gave us a representation over in terms of our E7, 1 minus PE7. So we should be able to work it out from the previous slide.
But I see no scalar product.
Okay, so I think this should be if you wanted to define this inner product, you could. Where I already defined a notion of Hermitian conjugate, right? So you could just take a Hermitian conjugate of this space, multiply it by another copy of the space, and then take the real part. Or
yes, your involution that you gave us would define that for us. We can take two then. I mean, we know what it is on the reals, the complex, and the quaternions. The less familiar one would be the octonions, and I think you've defined it there.
Okay. All right. So, right. So now on the left hand, okay. So the goal now is that we've got all of these irreducible representations in the standard model. And the game that Beth and I are trying to play is we're going to see, we've got this partitioning now into blocks, which is, and this is an important point, it is coming from octonionic structure. And so now the game is to see if we can find an embedding of these irreducible representations into the space, and if we can find some simple transformation rule, the simplest possible transformation rule in order to make have this embedding. Okay. So here on the left-hand side are the irreps from the standard model that we want to describe. So it has all of the standard models irreps that we reviewed earlier, except for the Higgs. So I haven't included the Higgs here. And on the right-hand side is our algebra. Now, in our upcoming paper, Beth and I write down a generic element of the standard model's infinitesimal SU3 cross SU2 cross U1 over Z6 symmetries like this, which we call LSM. Here, the lambdas are elements of the octonionic derivation algebra. Okay, so this is how we write down an element of the algebra. And then we have this element LSM act on our H16C space in the following way. So here's how the diagonal blocks transform. Here's how the outer off diagonals transform, and here's how the inner off diagonals transform. So this is, I would say, a relatively simple action. Now, under this action, we find that the dark green blocks transform as left-handed quarks. The light green blocks transform as left-handed leptons. The dark blue blocks transform as right-handed quarks. So now we're at the point where we've covered almost all of the off-diagonal blocks. And the only fermions that we have left to embed are the right-handed leptons. So we find that the last off-diagonal blocks do in fact transform as right-handed leptons, but they only give us one generation, not three. So we're missing an embedding for two generations of right-handed leptons. Okay. So next when we find, so we're just going to leave the fermions for now, and we're going to move on to the bosons. So next we find an object which is expected to eventually transform as a lepton's four momentum. And I say that because in this talk I haven't specified how the space-time symmetries are applied. So this was not part of the standard model's original particle content that we listed earlier, but it does appear within a momentum space representation of the standard model's covariant derivative. So in the next block, we find a similar four momentum for quarks, together with representations transforming as a full set of gluons. In this bottom diagonal block, we have elements transforming as do electroweak bosons, although we in fact have too many of these representations this time. Okay, so if we stop now, we see that we have 232 real degrees of freedom transforming under GSM in accordance with the standard model. So this is a majority of the 252 we would need if the standard model were to include these momentum operators and three generations of right-handed neutrinos.
Can I ask from some clarification? This group is an automorphism of this algebra of RCHO? What is it? Is it an automorphism?
Yeah, so that's a good question. So this LSM that we are using actually came from the earlier model that Mia and I wrote down, where we actually started with the spin. It was a spin 10 model. So it's we took it from that, and then what I did was I included these idempotents. It is a representation. What you can say is that it is a representation of that Lie algebra, but there potentially could be many different ways that you could, in this scheme, there are many different ways that you could write down that Lie algebra using the division algebras. And so what we're doing in this project is we're basically just trying something and seeing, or trying many different things and seeing basically, can you, when you play around with these things, can you get the standard model's irreducible representations to fit within the blocks? So I wouldn't say that this is coming from, you know, a nice mathematical principle. Basically, we're looking at this Peirce decomposition, and we're seeing, we're basically trying different embeddings. And so far, the one that we are presenting here is the one that was so far the simplest that we could find.
This RCHO, so suppose I take the algebra generated by RCHO, okay? It is some finitely generated algebra, okay? Because you start from a finite number. So within this algebra, can I write down the operators for the standard model?
So
marking is inner automorphism or outer automorphism?
Okay, so let's just go back to that, to where we wrote it down. So I'm not really sure I understand the question. So
That's good, that's good.
So the elements that we wrote down here are all written in terms of octonions and quaternions, and they yeah, and
Okay.
yeah. So I'm not so yeah, I'm not really sure what your question is.
So I can ask this, following question. You have written down this equation gives the Lie algebra of this group in terms of elements of the octonion or the RCHO algebra. Okay, so I can discard RCHO algebra and look at the algebra generated by the Lie algebra of these elements. No, why do I need the RCHO at all?
So then, okay, so you're saying, yeah, okay, so yeah, so basically this is what I was talking about earlier in the talk, was that the point of, just go back. The point is, if we were to just start with, let's see. What you can see here, one thing to say is that what you can see here in this element LSM is that it is, if you look at the first term is essentially octonionic. So these lambdas live in the derivation algebra of the octonions. In fact, this SU3, the lambdas are given by the subalgebra of G2, which leaves that a single octonionic imaginary unit constant. So in other words, it fixes S. In the second term, you can see that this is generated by quaternions. And then the U1, of course, that would have been nice if it somehow had something to do with the complex numbers. But the idea or the motivation behind this is that this, instead of having something like SU5, for example, the separation between the different groups is supposed to come from the different division algebras. So the fact that there's extra structure here, and so we're trying to capitalize on this extra structure in order to, for example, get things like different groups, or in this case, we had in the case of the Peirce decomposition, the extra octonionic structure. So this is one of the biggest reasons why we're using octonions, is that the irreducible representations seem to be obeying the Peirce decomposition, which is given by the octonions.
Just to clarify,
if we didn't have the octonions, then I wouldn't see how you would come up with this Peirce decomposition.
right. Just to clarify, the E7 is the one that is left invariant by the SU3 in the octonions.
Well, so it doesn't, so I should have made a comment
I
about
mean,
that at
the
top.
G2 has a 7-dimensional representation, and one element of that, if I leave it invariant, I get an SU3, yeah?
SU3.
And that's
exactly.
the SU3 you're referring to.
Exactly.
Okay.
So, and when I wrote down those idempotents, I used E7 as a specific example, but of course, any octonionic imaginary unit would do equally as well. Yeah.
Sure, but then, and it's the one that leaves that invariant, that's your SU3, yeah?
Exactly. That's where
the
the lambdas come from that I pointed out before. Yeah. So I guess
you had more projectors. That was one of your projectors. You had one minus some left action of that.
So we're using all 4 of them here. So there's little s star, big S, and big S star, and this Peirce decomposition that we have gives you all combinations. So that's how these blocks arose. Was that you hit the algebra on either side?
On left of okay, I see it. Yeah. Okay.
So I guess so this is a really good question about why is the octonion, or like where is the octonionic structure? Why is it useful? And I think one of the non-trivial things about what we're pointing out here today is that there's the octonionic structure gives you this Peirce decomposition, and it seems non-trivial to me that the standard models irreps to some extent seem to be obeying the decomposition, at least in the way that we're writing down the embedding. Okay, so so where were we? We were at this point where we said that, okay, so we, in this bottom block here, we've got elements which transform as do the electroweak gauge bosons, but we've got too many.
So when you said you had 232 here, are you counting these too many, or you're just?
No, I'm just counting the ones that worked. So there's 232 exactly. So there's 232 that worked, and then if you were to include these momentum operators and on top of it 3 generations of right-handed neutrinos, then the total would be 252. So so basically what we're demonstrating is an embedding which to a certain extent comes close to what we have in the standard model, but is obviously not exactly what we want. Okay, so now beyond this, there's some interesting patterns that emerge that you might have already seen for yourself. And that is, in particular, you notice that the bosonic objects, like 4 momenta and the gauge bosons, seem to live in the diagonal blocks that are colored here in orange. In fact, the extra 4 momentum blocks seem to be important because now these diagonal blocks appear to be describing a momentum space version of a covariant derivative. Now, if we were to, now for the off diagonal blocks, this is where the fermionic degrees of freedom are found. Okay. Now we're still missing 2 generations of right-handed leptons, and yet on the other hand, we have too many elements transforming as electroweak gauge bosons. So
are you going to put Higgs in there as well?
That's coming.
Okay, I see.
Yeah, there's a comment about that coming. Yeah, thank you. Right. So so the question is, have we hit a roadblock?
Sorry, Colt, was there not one diagonal block that you didn't mention?
Yes, that's also coming.
Sorry.
Yeah, it's okay. Yeah, thanks for asking. So now for some reason it's not letting me. There we go. There we go. Okay, now it's working. All right. Okay, so the question is this the end of the road for this particular embedding? And it's not clear. What I will point out, though, is that these Peirce blocks were based on one particular octonionic imaginary unit. And however, when we finally introduced to this electroweak block another octonionic imaginary unit, which is orthogonal to the first, then it can act to further split this electroweak block. And oddly enough, when we do that, the diagonal block now provides a suitable space for the electroweak bosons, and the off diagonals now have the right dimension to describe the missing 2 generations of right-handed leptons. So the main source of difficulty at the moment is to understand how space-time symmetries should act on these spaces without overcomplicating the transformation rule. Okay.
May I
So
ask another question? So you've put this together using E7. Would it have made a difference if you chose a different octonion?
No. No, exactly. It doesn't matter. It's any octonion will octonionic imaginary unit will do for this.
Okay, thank you.
So if we could get this electroweak sector working, then there would only remain 8 real degrees of freedom left in the algebra. So it would be actually quite a tight fit. And an obvious possibility for these 8 real degrees of freedom, so those are the 2 boxes in white, would be 2 Higgs fields. However, it's too early to say anything definitive about this at this point. Okay, so for the last part of this talk, I want to tell you about a couple of new directions that we'd like to look into. One relates to coloring projective measurements. So I mentioned before that I would explain to you where these octonionic idempotents come from. So these are the idempotents that give us our Peirce decomposition. Now, it so happens that every time that you have octonions multiplying octonions or quaternions multiplying quaternions, then there's readily a Clifford algebra that arises. So take, for example, left multiplication by the octonions. So here's what that looks like. As a Clifford algebra, we've got a 0 vector at the bottom. Then we've got 1 vectors, which can be given by left multiplication by an octonionic imaginary unit. So we can write left multiplication algebra, left multiplication using this notation here, or we can write it using the big L notation that we used from earlier. So it's the same thing. So this goes from EJ1 up to EJ6. And then next we have bivectors and 3 vectors, and you keep on going up until you get to the 6 vector. Well, hold on, you might say, what happened to EJ7? Don't the octonions have 7 imaginary units? Well, it turns out that you can show that the 6 vector always gives the same linear map as EJ7 up to a sign. So when you populate the generating space with multiplication by orthogonal imaginary units, then the resulting Clifford algebra has a natural way to single out 1 octonionic imaginary unit. So the octonionic imaginary unit here up at the top is an analog of the gamma 5 element familiar from the Dirac algebra. So just like with chirality projectors in the Dirac algebra, you can also build octonionic projectors with this EJ7. And in fact, that's how we constructed little s and little s star. Now, incidentally, it's easy to show that the left multiplication algebra of the octonions is isomorphic to the Clifford algebra CL06. So as you know, the octonions can also be right multiplied by octonions. So there's another way of writing down this CL6. And we have the exact same Clifford algebra structure as before, except now we're generating it using right multiplication. Now, one interesting property about the octonions, which you might not have expected, is that whenever you right multiply an octonion by an octonion, you can always re-express that map with chains of octonions coming in from the left. So you'll notice that this, so for example, we've got right multiplication here by E7 up at the top. And you can always rewrite it like this, where it is now re-expressed so that everything you'll see is now coming in from the left. So this is in fact where the capital S and capital S star idempotents came from. They're analogs of the chirality projectors, this time for an octonionic imaginary being multiplied from the right. So being able to re-express right multiplication by left multiplication is also a feature of the complex numbers and the real numbers because these are commutative algebras. However, it is not true for the quaternions. So let's consider now left and right multiplication of the quaternions. Then we can left multiply the imaginary, so we can left multiply imaginary units of the quaternions, epsilon j1 and epsilon j2. And these give us our 1 vectors. And together they make just one bivector, which then gives us plus or minus epsilon j3. So again, when you populate the generating space with multiplication by imaginary units, then the left multiplication algebra of the quaternions has a natural way to isolate one imaginary unit. And now, of course, you can right multiply epsilon j1 and epsilon j2, and you find a similar pattern. Now, in the left multiplication case, we find that we have an incarnation of the Clifford algebra CL02, and the same goes for right multiplication. So in summary, the octonionic and quaternionic left multiplication algebras provide us with a set of 4 idempotents. For the octonions, we have little s star, capital S star. For the quaternions, we have now 2 new idempotents, little t star, capital T, and capital T star. Now, as we just mentioned, these 3 sets are expressible. There are 3 sets of these which are expressible in terms of left multiplication. So it's these ones. So these 3 out of 4 sets live in RCHO's left multiplication algebra. Okay. So now we're in a position to make a comment about projective measurements. Namely, here are the idempotents that we obtain by taking all combinations of these 3 sets of projectors. And when we apply them to our list of fermions, we notice that they project down on measurable states. Namely, the first idempotent projects down on a helicity plus lepton, the second idempotent on a helicity minus lepton, then helicity plus baryon, helicity minus baryon, isospin up for left-handed fermions, isospin down for left-handed fermions, isospin up type for right-handed fermions, and isospin down type for right-handed fermions. So the reason why I'm pointing this out is that I find it interesting that missing from the list are projections on color. Okay, and so there's one final note that I'd like to make. So far we, yep.
Sorry, quick question. So no projection on color. So you mean when baryon up, you don't change the color?
Exactly. So it will so that projection will project down on the space of quarks, but it won't project down on. It won't specify which color.
I see. Okay.
Yeah. Okay. So right. So so far we've been focusing on RCHO's left multiplication algebra, and this is isomorphic to CL8. However, RCHO's full multiplication algebra, including both left and right multiplication, is given by CL8 cross CL2. So a direction that we just started looking into is whether or not this extra CL2 piece could somehow be used to describe a vierbein or perhaps something similar concept to replace it. The idea, of course, would be that if we could upgrade our connection to also include a spin connection, then we might have the basic tools to finally include gravity. Okay.
Sorry, if I may, could you go back to a few slides back? So the fact that you don't project on color, does it have anything to do with what Denjo asked before, that E7 leaves SU3?
Yes, exactly.
Change?
Yes, exactly.
Oh,
Yeah, that's an excellent question. It does, and that's right. So basically, what we're doing in order to build these projectors is basically there's all this Clifford algebraic substructure within this algebra, and this Clifford algebraic substructure, as I mentioned, gives you these volume elements or the objects analogous to gamma 5, and we get them in different situations. You get one for the quaternions, you get ones from the octonions, and so basically we're building these projectors with those analogs of the chirality projectors. And it's interesting that you can measure things like helicity and isospin, but within those chirality projectors, it doesn't give you a projector which will project down on color.
Mhm. I see. Good. Thank you.
Yeah. No problem. Okay. So to summarize our results, we found a relatively simple action on the Hermitian part of RCHO's left multiplication algebra. This gave us 232 out of an expected 252 degrees of freedom transforming under GSM in accordance with the standard model when we augment the vector space with momentum operators and right-handed neutrinos. It is a non-trivial finding that these irreps obey a Peirce decomposition deriving from a single octonionic imaginary unit. It's also non-trivial that this embedding displays a clean separation between bosonic and fermionic degrees of freedom, with bosonic covariant derivative occupying the diagonal blocks and the fermionic degrees of freedom occupying the off-diagonal blocks. And that's all I have to say.
Okay, thank you very
Are
much.
these all massless particles?
I'm sorry.
Are these?
So at this point we haven't explicitly constructed a Higgs. So there were 8 real degrees of freedom left over in the algebra, and one possibility for those would be to that those could represent 2 Higgs fields, but getting this whole model to work is, we're not at that point yet where we've we've specified Higgs fields and then written down a Lagrangian where you can have mass terms.
So my question was the following: the helicity is not in Lorentz invariant for a massive particle. So, but the helicity is included. The helicity is included in this RCHO scheme. So what happens under a Lorentz transformation?
So this is something that we have also written down. So in one of the earlier slides, we wrote down LSM and its action on this space, but you can also write down what an SL2C operator looks like and then have it act on the space. And it has, so again, most of it works out nicely, except there's forever this electroweak section, which just is a major headache. So I didn't include it in this talk because it just adds complication, but there's an analogous action to what we wrote down for SL2C. And again, the majority of the states transform as you would hope, and the electroweak part is just a problem.
But the space-time coordinates is not appearing in your discussion. X.
Right. So we're not putting this on a manifold or anything at this point. This is entirely algebraic, and I should mention that the Lorentz group is actually a natural group for RCHO, in that SO31 is part of the automorphisms of RCHO. In fact, the SO31 is the automorphism group of the complex quaternions, which is one of the reasons why I started looking at this in the first place. It turns out, I haven't described it here, but you can write down all of the representations of the standard model, all of the Lorentz representations of the standard model. So scalar spinners, 4 vectors, and the field string tensor, you can write them in terms of just the complex quaternions. Right, and then the automorphism group of the complex quaternions is the Lorentz group. So the natural extension of that is just to see what happens. So the complex quaternions, of course, is equal to C cross H is equal to R cross C cross H. And so then the obvious extension is just to say, well, what happens if I add O to this? So that's why I started looking at it. And of course, the octonions, their automorphism group is G2, and their subgroup SU3 seems to do a nice job of describing SU3 color.
As you pointed out at the beginning, there are discrete symmetries to the standard model. There's this,
Yes.
I think, a Z6.
Oh,
Can
that
you-
one, okay.
Can you see where that Z6 might be coming out?
I wouldn't, so you can see where
Why
the
does
Z6
it do
comes from,
nothing?
But I wouldn't say it's necessarily specific to the division algebras. So the Z6, you can, like if you started in SU5, you can use the division algebras to take you from SU5 down to SU3 cross SU2 cross U1 over Z6. But I would say that's kind of more of a feature of the way of SU5 and the way the standard model lives in that than it really has to do with the division algebras.
Is the Z6 a Z3 cross Z2? Is that what it is?
I'm not sure. You can basically you can look at the standard model's particle content, and then you can find 6 objects which are non-trivial, that all like individually non-trivial in each group, and then when you put them together, then they become trivial.
Yes, yeah.
The Z6 is the following. You take Z3 of SU3,
Yes,
Z2
yes,
of SU2, and
yes.
so that is the product has period 6. So you take a period 6 element of U1, and the whole thing is what causes this. That's invariance. Yeah.
But is it Z6 or is it Z3 cross Z2?
Cross something from the U1 part.
It's cross something on the U1 part. Okay.
Because it is coming in magnetic monopole, non-abelian monopole theory.
Okay. But they should be. I mean, your Peirce decomposition should show that should be invariant under this discrete symmetry.
Yeah, the moment you choose the representations, as she has got, the Z6 factors out automatically. Because in these representations, Z6 goes to 1.
It should do, yeah. But I'm presuming that that this Peirce decomposition is invariant under that Z6, that it does nothing on it.
Yeah.
That the Z3 and Z2 are just floating in there.
Yeah.
Yeah.
Should be like that. But I still do not understand Poincare representations. What about boosts? Where are they? Okay. The representations are infinite dimensional Poincare.
Which, as she's, but this is just a particle content. If you were in the massless sector, then that would be fine.
The Lorentz group is contained in there.
No, I don't.
It's SL2C. That's what Cole said. It's SL2C. It's the complex quaternions.
That's at a given point. I mean, index lambda.
It's not a unitary representation, but it's a finite dimensional representation of Lorentz group.
Not on the field. If you take a spinor field, okay, with an index, so there's an SL2C action on the index, okay, which is half 0 or 0 half.
Yes.
However, when you take also, but it also acts on the argument of the field, X.
But she doesn't have any X.
I'm not writing down a field theory.
Cole hasn't put any space-time dependence in at all.
There is no space-time at all.
Then it is not the correct group for the standard model.
No, that doesn't
It's the
follow.
internal symmetry of the standard model.
Yeah, it's just the internal symmetries. There's more to be put in here, which hasn't yet been put in.
I don't agree. SL2C is not an internal symmetry.
No, it isn't. But these are.
Sorry?
But these are.
But so are we I'm being polemical, but in the standard model, let's take the standard model, doesn't matter. Take a spin half field, say Dirac particle.
Mm-hmm.
There is an SL2C action which transforms the index by, let us say, half 0 plus 0 half. It also transforms the argument of that by the PSL2C action. Okay. Now, this doesn't look unitary, but there is a scalar product you can find such that, which is not a standard one, such that this action is actually unitary. Okay. This is Wigner's function construction using boost operators. That is an infinite dimensional representation. Okay. And it involves argument of X also getting transformed. It is for this group that the Laplace Orevit's theorem applied. that you can't
Sure.
combine it with internal symmetries.
Sure.
Ah.
Sure.
Here, I don't know what is happening.
Yeah,
Just
because
like an index, I don't know what it is. Okay?
this is the group structure of the standard model being discussed.
Yeah.
It's not
So I didn't,
as much as
I
you.
didn't actually write down an action for SL2C at all. So the representations I was talking about here was entirely GSM. I do understand what you're saying. Like we eventually, you know, at some point, if we're going to have SL2C representations, we're going to have and if they need to be unitary, then we're going to need to have an infinite dimensional representation. That's fine, but it's just not what was done here.
Does this SL2C commute with internal, what I may call internal symmetries?
So yeah, so the original, so again, this is not something that I wrote into this talk. So I wasn't describing that at all, but in separate work that I've written that we've done on this, you can write down an SL2C action. Like I mentioned before, it does commute with the internal symmetries, so it doesn't run into the Kalman-Mendeleev theorem. But again, like I said, it works very nicely on most of the irreducible representations, but the electroweak sector is forever a thorn in my side.
Okay.
Can I ask an
Related
elementary
to
question?
Fesa-Gursi's work, no?
I'm sorry?
Fesa-Gursi also had octonionic algebras and their stability groups as G2, I think. Yeah.
Gursi?
Yes.
Fesa-Gursi, yes. Yes. So Murat Günaydın and Fesa-Gursi were the first in the 1970s that I'm aware of to have identified quarks within a subset of the octonions transforming under SU3 in the which is a subset of G2.
Okay.
Or subalgebra of G2 rather.
Okay.
Can I go back to something that was said right at the beginning, and I just missed the answer. You had this isomorphism between RCHO and the CL8.
Or the left multiplication algebra, yeah.
Yeah, but CL8 is, I mean, it's a matrix algebra, so it's associative, but octonion multiplication
exactly.
is not. So what happens to the non-associativity of octonions under that isomorphism?
Yes, so okay, so let me, so this is, so the question you're asking is the one that I find the most difficult to explain, but this might take me a while to get back here. Let's see if I can do it quicker. So it was basically somewhere around these slides here. Where can I find this? So you can think of this as there's kind of like two algebras happening at the same time. It's so you can think of, so the analogy is like you can think of in quantum theory, there's the operation of having an operator act on a state to give you a new state. And that's kind of like the analog of RCHO's multiplication algebra, and that's where you see the non-associativity. But then there's also a separate concept that happens for us in quantum theory at the same time. And it doesn't kind of, you know, ruin anything else or do anything malicious to the other, you know, operation that I just described. It's compatible with it. And that concept is the concept of combining operators together via composition. So you can take two operators, compose them together, and it gives you another operator. And you can think of that as a notion of multiplication. So what's happening with this left multiplication algebra, so there's a kind of a parallel concept here where we have elements of RCHO multiplying onto each other. So that is still in effect. But anytime that you've got a multiplication like this, there's also a simultaneous algebra happening at the same time, which is compatible with it. And that's this left multiplication algebra, or it's full multiplication algebra. And in that case, when you consider multiplication as a composition of maps, then that is naturally associative because maps are associative by definition. And so that's how you get these Clifford algebras. Clifford algebras are also associative, and that's where the Clifford algebra structure comes from. So I think people, it's interesting because people really focus on the non-associativity of the octonions, and that's, you know, it's natural because that's what they're most famous for. But an interesting thing, so we're not kind of suppressing anything. We're just using a different part of the natural structure that comes up. You know, for example, another point to be made is that with Lie algebras, that's also a non-associative. Lie algebras are generically non-associative, and you know, we don't focus when we deal with Lie algebras all the time, and we don't focus on their non-associativity. Like it is, you know, it's somehow not as important. But with the octonions, people really feel they need to see the non-associativity.
Just to understand a little bit better, if I put a third one in here, LW,
Yes.
and I compose them.
Yeah.
You are saying that the order of the brackets, I won't need to worry about it.
Yes, when it's okay. So this is a point where it would have been nice to have a pen. Okay, so
Because the right hand, side of your line there, I wouldn't
Yes.
needed to worry about it if I had a W on it. So, but on the left hand side, you're saying I don't need to worry about it.
I'm saying that. So when you're writing things in terms of this notation with the capital L's, like capital LX and capital LY, in that case, you don't need to write down the brackets. But when you write it out on the right-hand side, the way it's written there, then the brackets are important.
But if I take the left-hand side and I take an LW with this, with another bracket on it, I would naturally consider it as a W acting on this XYZ.
Exactly, where the brackets are nesting, going from inside to outside.
Yes, but now if I combined first my W and X, and then combine that with Y, there would be a different object. It would be the same object here on the right.
Yes,
but
no, because the object on the right hand side, the brackets would be different. So, for example,
but it's the same object on the left, so it should be the same object on the right. I'm assuming that it's actually that I would need a different object on the left to represent a different ordering of the brackets on the right.
Different position of the brackets.
Can I make it?
I think it might be helpful if we could write things down, because I think we're going to run into some confusion. But so one thing to say is that no matter how crazy of brackets that you have, so the way if you were to just take like an LX, LY, and keep on going, for example, then the way that it would be written down on the right hand side is the brackets would be nested one after the other. I don't know if you know what I'm saying, but
yes, I do. They will always be nested on the left. If I do the left-hand side.
If you were to throw at me something that has a crazier bracketing structure
on the right,
then you can. It turns out because of you can always rewrite those maps so that they are put into a nested structure.
Oh, yeah, I can use the associator of this to reorganize this.
Or for example,
you could think of LY as a composition of two L's and stick it in that formula, and then you can induce what you want.
Yes, exactly.
Yeah.
Can I ask a question?
Please,
what is the state on, you said this is a Caesar algebra. So what is an example of a state? And suppose I do a JNS construction, I will get a representation on a vector space, complex vector space. What is it?
So you could, so this is again like something we haven't done yet, but in principle, I can't see why you couldn't. If you take the irreducible representations that we wrote out in the Peirce decomposition of this, in this, where we wrote out all the states, Those are all complex vector spaces. Like they live in an algebra, but it's still a complex vector space. And we have a notion of Hermitian conjugate. So you can just make an inner product with that.
It'll just be a finite dimensional representation, roughly like one of the standard model ones, except to be complicated.
Exactly.
One needs a
Yes.
state on this algebra. What is a state?
You don't have any states yet, right?
Just one example. I don't see any state here.
We're jumping ahead, Bob. We haven't got the states yet.
Okay. All right. See, by the way, U star, the fact that there's a star doesn't mean that it is a C-star algebra. U star U, there is an issue of spectral radius of this object, to make it sure that it is positive operator in the algebra. So how does one define a positive operator in the algebra? Okay. And from what I know, it is defined by what is called spectral radius.
Yeah, but there's a norm. It's a normed algebra, so they're okay. These are normed algebras, so you have a notion of positivity related to the star, which all works as far as I would think.
In that case, there is no JNS construction.
These are, well, the other thing to say, which was just mentioned too, is that, these are the same irreducible representations as what's in the standard model. So it's the exact same structure as you would have in the standard model. Like the irreducible representations are the same. Right.
I should leave. Thanks. It was a good talk. Okay.
Thank you. Thank you for your question.
A lot of ideas.
I have a question, sorry.
Yes, go ahead.
Is there any free room for dark matter? I mean, is there any way to go beyond the standard model? And,
Yeah, it's a good question. So there's this, coming from the, coming from the purely algebraic side, there's been this question that had bothered me for a while, is that we've only, so in this construction, we're only considering the left multiplication algebra. And the nice thing about that is it kind of roughly gives you the size of the standard models, irreducible representations. But then there's right multiplication, presumably from a mathematically aesthetic point of view, you'd also want to include the right multiplication algebra, in which case you get an extra factor of CL2. So there's kind of two ideas that came up with what to do with the CL2. Basically, including this factor of CL2 quadruples the size of your algebra. So one option could be that somehow that this extra, you might hope for those extra dimensions to give you dark matter. Another option, which is what I mentioned in this talk, was that maybe you could use that extra factor of CL2 to somehow build a vierbein, but again, it's too early. It's too early to say.
But there is no way to couple left and right multiplication algebra, I guess. I mean, they are independent, like two copies independently. Don't talk each other, right?
No, well, so it's not that simple, and that's what's kind of nice about this, is that in the case of the complex quaternions, they do decouple. So you'll have a copy of CL2 coming from the left and a copy of CL2 coming from the right, and they're in some sense completely independent. However, with the octonionic sector, then anytime that so there's a CL6 coming from the left. But it so happens that with right multiplication on the octonions, you can always re-express it as left multiplication. So the CL6 that you get from the right is actually the same CL6 that you get from the left. So there's some highly non-trivial structure between how left and right multiplication is related, depending on whether you're looking at octonions or quaternions.
Thank you.
Thanks very much, Nicole. I'm going to go now, so bye.
Yeah. Can I ask about G?
Thank you for all your questions.
Yeah, thanks. I wanted to know about where does G2 play a role here?
So G2 is the automorphisms, as you know,
of the octonions, yeah.
Octonion, automorphisms, and if you take G2 and you fix an octonionic imaginary unit, then that gives you SU3. And that is SU3, those were the lambdas that were living inside the LSM.
Yes.
So you can either look at it as isolating a single octonionic imaginary, or you can see it as fixing those chirality projectors, S, little s and big S.
But I mean, the thing is, I've never heard of G2 as one of the candidate groups for grand unification. Doesn't quite seem to fit into that setting.
Oh, it's it's not.
Might have guessed
it's not big enough. So G2 is not big enough in order to house everything. So the only piece that we're using from G2 is the SU3 part.
It's only the SU3 part of G2 that you're using.
Exactly. Yeah.
Yes, I mean it also has SU2s in there, or SO3s
Exactly. There's,
and
right.
U1.
So there's other maximal
Yeah.
subgroups in there. And there's an SU2 cross SU2, which also
and you
lives
could
there.
use
And
more than one representation if you wanted
yeah.
your.
So that is a route that I have tried at some point, but you know,
Okay.
I didn't get very far with it, and mostly because the representations that those SU2s give are not the representations that you need. It gives you some other representations that weren't helpful.
Okay, right.
Yeah.
Okay. Very good. Are there other questions? Well, thank you again. I'm going to stop the recording, and thank you very much for a fascinating talk and insight into this new world. Okay.
No, well, yeah, thank you so much for all of your questions.
So